All right, good morning, everybody. I hope you guys are doing well today. Before we get started with 6.03, because I don't really have any major announcements regarding anything at this point in time, any specific questions with 6.01 or 6.02 at all? Anything you want me to go over? Yeah, so parallel vectors occur. Well, let me get my book out because I'm thinking of perpendicular, um, which ones are orthogonal? Is it parallel or perpendicular? Because now all of a sudden I'm blanking. Perpendicular. Okay, so parallel. Let me go back. Did we talk about parallel ones? I'm not sure if we did. I don't actually see it addressed in the book at all. I see perpendicular. So just give me a moment. We'll do some digging. Yeah, that's all I have notes for too. Was there a question that had parallel? Because I think like the parallel ones are almost kind of like equivalent. Okay, let me go back and check out the quiz. The last two questions, you say, huh? Okay. Well, let's take a look at the last one. You have to see if the slopes of the given vectors are the same. Okay. So if I take a look, are we comparing it with the origin? Let's see. We'll Google it because I do see the questions there. if they are multiples of one another. That's what I'm thinking too, because if they are equivalent, which means that you basically are just multiplying through by like the length or the magnitude would be the same. Let's check. I found an explanation here online. My computer's just really slow. Sorry, guys. Okay. I didn't realize that we threw parallel out there without talking about it because I wasn't really aware of how to find those either. I knew the perpendicular because those are your orthogonal. And it looks like Rebecca's right with your scalar multiple. So it appears that for two vectors x and y to be parallel, x has to equal y times some multiple, where c is any real number. So basically, if we create fractions, we should get the common scale factor between them. So for example, if I were to set up 15 over 5 and 3 over 1, both of those would have a scale factor of 1/3 or 3, depending how you look at it, right? Every other one would not give you the same result, because there you would get a -3 and here's a +3. So yes, you get 3, but they're opposite signs. 36 over 5 is not the same as 6 over 1, and 24 over 5 is not the same as 4 over 1. So it does look to be that vectors will be parallel if one of them is a multiple of the other. So Rebecca's understanding there is correct. So when we take a look at the last question from the homework, let me bring that up because I think that's the one that actually turned out to be parallel. So the first thing I would do from the quiz, like if you had this question on a quiz or homework, is I would check for the parallel first, because that is just setting up and looking for your scale factors. So setting up your ratios. So 14 over -7, or the other way around. Does that equal -4 over 2? Because if it does, then they're going to be parallel to each other. If it doesn't, then I would go and check to see if they are orthogonal by using the dot product. So this one actually turns out to be a -2 ratio each time. So all I have to do is multiply through u by a -2, and that's going to give me a v. So u equals a -2v technically, right? So because of that, they will be parallel on the last question. Okay, and I don't know what number that question was. Was it question 5, I think? Yeah. Okay. All right. Whew. Glad we got that straightened out. Any other questions with that parallel vectors? Sorry, guys, that I didn't catch that sooner. Looks like you guys have good problem solving skills though. You do the same thing that I do when you're not sure. You either go to the book. If you can't find it there, you hit up Google and you keep your fingers crossed that Google knows what it's talking about, which is generally the way it is most of the time. Google's usually going to steer us in the right direction. Oh, thank you. So the resource videos, again, like I had mentioned, I haven't actually watched those resource videos for quite some time. It was like months and months ago over the summer. So it does look like some of the resource videos explain the parallel vectors as well. So that was good. Okay. Any other questions before we take a look at 6.03? we're a little bit ahead of the game as well as far as the pacing goes on the calendar. So for 6.03, if we don't finish it all today, it's not that big of a deal. We can wrap up with it on Thursday. All right, so grab those calculators, your graphing calculators, and then if you don't have a graphing calculator, we'll have to look on Desmos. There's a parametric version of Desmos that they will allow us to graph in. We're going to learn about a new mode today. Yay! So up to this point, we've worked with like degree and radian, but it's always been in our function mode. Today we're going to start looking and exploring different realms here. So we're not necessarily going to be looking at functions. We're going to be looking at parametric equations and parametric curves. So real quick before we begin, I want to go ahead and show you how you can switch to parametric mode. I don't believe it matters if you're in degree or radians there, but when you go to mode, you're going to want to scroll down to the fourth option where it says function, and you want to scroll over to the PAR. PAR stands for parametric, right? And that is the mode that we will be working in for lesson 6.03. Right next to parametric, you're going to see POL. POL stands for polar mode. We will be working in polar mode in the last part of the unit. So we will be exploring that other option as well in Unit 6 here. Okay, but for today, we're mainly focusing in that parametric mode. So parametric, you have two equations. You have an x equals and a y equals, and the variable that they use is t. So that dependent variable is going to be the t in each of those equations. T is what we are defining as our parameter, right? So we do have intervals that we're given for our parametric curve, so we do want to pay attention to the parameters that we are graphing in. All right, so for example, I have the parametric equations given here for x and y, and then I have three different graphs that I can create based off of the different parameters that are given. So this is what we call the parameter interval. Okay, here are the parametric equations. T in there, so t is that dependent variable. T is what we call the parameter, and then the actual graph is what we call the parametric curve. So lots of different vocabulary terms there. Now, the good news is it's actually not too bad if we can remember some of our basic algebra. So the first thing we're going to do is our charts are extended a little bit, our table of values here. We're going to include t because that's now our dependent or independent variable. Sorry. And then x and y, I apologize. T is the independent variable. It's what you choose your numbers from according to the interval you're given. And then x and y are dependent on that t. So let's take some time and fill these charts out. This first one is for A, the second chart's for B, the third chart's for C. We're using these two equations for x and y for every chart. So as soon as we fill out this first chart, we can actually transfer some of those numbers over to the second one and the third one as well. So we're going to work smarter, not harder. So let's fill out this first table of values and then we'll transfer it to the other two charts. So let's divide and conquer. Everyone pick a number here that you want to substitute in to either x and y, and when you have an output value, put it in the chart, and then I will start copying that over to the other boxes. So the first step here is simple substitution. We're going to substitute those values in for the x equation and the y equation and simplify. Okay, and as you guys are filling in this first table, I am checking your work. I do have the answer next to me, so I'm making sure you guys are doing it correctly before I transfer it to the other charts. Okay, looks good. I'm going to transfer these last couple numbers over. Move to part B, which is the middle chart, and we have a few extras that we get to add in. So it looks like we can substitute in the values for t equaling 2 and t equaling 3. Awesome. So essentially what we did with the substitution process is we created ordered pairs for us to graph. Now each ordered pair is going to give us a different kind of piece of the graph, or I should say each choice here, so A, B, and C, are going to give us different parts of that graph. We only are interested in the intervals for which we have the ordered pairs for. So if I advance the screen right here, we can see that overall it's the same kind of graph, but it's just different chunks of it based on the interval that we were told to look at. So we almost have a parabola there, kind of turned on the side, but we're looking at different pieces of that. Any questions with the substitution part and the graphing piece of that? So really, if you had a graph by hand, it's not too difficult. You just substitute to create a bunch of ordered pairs and then plot the ordered pairs to connect. All right, let's talk about something called eliminating the parameter. So if we're given parametric equations, we can actually perform a process called eliminate the parameter so that we can create an equation in rectangular form. And though the rectangular form is what we're used to, it's just the x and the y variables. The t is no longer there because we eliminated it, right? So to eliminate the parameter, essentially what we're doing is the substitution property. We need to solve for t in one of our equations. Now generally I like to solve for t in the x equals equation, because when we substitute that over to the y, we don't have to necessarily isolate the y. However, maybe it's not always easiest to isolate the t in that first equation. So it doesn't really matter to me which equation do we want to work with to isolate the t in. Do you want to isolate it in the x equation, or do you want to isolate it in the y equation? All right, so to isolate t in this first one here, what steps do we need to take? So remember, we want to get t by itself. Start by subtracting the 1. Yep. Divide by -2. All right, once we know what t is, we're going to substitute that into the other equation. So we'll have y equals 2 minus, and now instead of our t, we're going to place in the x minus 1 all over -2. Technically, I can go ahead and take out, if we can leave our answer just like that, that's fine. But I'm going to take out the -1/2 from the denominator. And maybe we can even simplify that a bit further. So that technically, if I take out the -1/2, we'll go ahead and put in a +1/2 there, right? And that's what we're going to distribute through the parentheses. So it looks like, because we're used to writing things in slope-intercept form, right, that would be a 1/2 x plus 1½ after I combine those like terms at the end. Okay. We now put this parametric equations into our rectangular form there. So we eliminated the parameter and we changed that into our function form that we're used to graphing with. All right, let me show you exactly how to enter this on your calculator in the parametric mode to verify that we get the same graph of 1/2 x plus 1½ So what I want you to do is, if you haven't done so already, go to your mode, change it to parametric, and hit your y equals button. You're going to notice that instead of just having y equals, you now have different groupings. There are 4 different groupings that are technically on my screen here, well, 3½. You'll have an x and a y. So you want to type in your x equals 1 minus 2t, and the t button is just this x t theta n button right here. So the same one you would press to get your x is what you're now going to press to get the t. Because we switched modes, the calculator knows that that variable should be a t instead of an x. Okay, and then you just scroll down, type the 2 minus t in. I'm taking a look at our interval. There are no restrictions for t. It's going to -infinity to +infinity. So I do not need to change my window at all for what I'm looking at. So I'm just going to hit graph after that. Ta-da! Now it does stop there. I'm not sure why my calculator likes to cut it short, but it does in fact look like it is that line that has a y-intercept of 1 1/2 and a slope of 1/2. So it matches up nicely to that rectangular equation that we created. Even though mine got cut off. But that could be because my window might not be set up correctly. Yeah, when I go to my window, I notice that I have it accidentally being cut off a little too soon. It's not going all the way to infinity. So we would technically have to change our max and mins to see the full thing, because right now we have it being cut off at -10, +10, and our t max is at a 2 pi. So if I change the t maximum, I think that might expand the viewing window a bit. But we don't need to play around with that quite right now, because we can still get the idea behind it, that what the graph should look like. Okay. But right here, the t min and the t max is your interval range, right? So technically we're looking for t starting at 0 and going to 2 pi. And I have it set at 2 pi because of a problem we'll be looking at later on down the road. So I had to change my interval there. Just for fun, I'll change it to 15 and hit graph again. And it did extend it a little bit further, but we can't really tell. So I think we'd have to play around with the window to get to see the entire thing. I'm not sure why it won't let you graph these eyes. It could just be something finicky on your calculator right now. We'll skip over this one. There's some other graphing ones. The good news is that the parametric equations that we're going to convert or change and graph, we don't necessarily need the graphing calculator for. They're going to be pretty basic, that if we can create a chart at least, we will be able to identify what the graph will look like. So it's not like any of the examples we're looking at in this lesson are going to be overly challenging by any means. We may want to fix it, and hopefully, fingers crossed, it gets fixed before some of our trig stuff though. Oh, well, speaking of trig, how we eliminate the parameter with trigonometry is we try to relate it back to our Pythagorean identity. Now, the most basic Pythagorean identity that we know is sine squared plus cosine squared equals 1, right? So we're actually going to use that same rule to try to help us convert and eliminate the parameter here. So what we're going to do this time is we're actually going to solve for cosine and sine t in each of our equations. So the first one, how do I get cosine t by itself? Yeah, divide by 2. So they kept it kind of nice and basic for us. And then how do we solve for sine t? Same idea. All right, now what I'm going to do is I'm going to go ahead and I'm going to substitute these into our Pythagorean identity. Now, this is a little bit different method than what the book did, but it's still going to result in the same answer. So it'll be kind of nice there. So the sine x, sine x should be my y, I think. Sorry, that should be a y, not an x there. Got a little bit sloppy. Technically, that should be a y here. Sorry about that. So we'll get y over 2 squared plus x over 2 squared, and if you want to swap these around, you can. So applying the squared on each piece will be a y squared over 4 plus an x squared over 4. And if I want to eliminate the fractions, what can I do at this point? Multiply everything by 4. Anybody know what shape this graph is going to be now that we eliminated the parameter? Y squared plus x squared equals 4. What is that the shape of? What graph shape is that? Not a parabola. If both of your variables are squared, think back to our geometry. Not a square. This is going to be the generic formula for a circle, right? So x squared plus y squared equals r squared is your generic formula for a circle. So I'm going to just backtrack a moment here. So from our geometry days, and that's with your circle centered at the origin, right? So in this case, our graph is going to be a circle centered at the origin, and it's going to have a radius of 2, right? Because 2 squared is the same as 4. So technically the r in this setup would be 2. Okay, let's go back and actually try to type this into our calculator. Oops, mine shut off. Let's do x equals 2 times cosine of t, and then y equals 2 times sine of t. And let's see if we can get the graph to appear. Oh, and take a look. Here is my interval from 0 to 2 pi. So when we go to the window, and my calculator's like broken now, but before you hit graph, jump over to the window and select your t min as 0 and your t max as 2 pi. So when you're in that window area, and to get there, it's just right here. Change that to 0 to 2 pi. So there's the equations. There's the window with your t min and t max set. And then there's the graph. What is your previous max set at? Like, what's the number? Because mine will change it to the integer value. Yep, that's the integer value for 2 pi, so that's fine. Nope, you're good. The t step you can just leave. We don't really change the t step too much. Is generally like what it's going up by if you were to create a table for it. You can make that 1. I just leave it whatever the calculator has it set as. All right, questions with how we got the rectangular coordinate equation there with just your x and your y, or how we verified the graph on the calculator. Isaias, did this one come out better for you? Check your dimensions. When you go into your window, do you see stuff like this? The other thing that you might want to check, and I don't know if it's going to make a difference or not, is are you in radian or degree mode? You are in radians. Darn. Okay. X is going to equal 2 cosine of t. So when I type this in, it's just 2 cosine of t, and then y equals 2 sine of t. All right, we have a couple people who are getting errors. Let me, on a side note, let me find the Desmos graphing calculator. And see if we can get that to work at least. Okay. So let me just check out this one and see if we can get it. Let's do x equals 2 cosine of t, y equals to. Okay, hold on. I'm not sure if this is the correct calculator I want to have you guys in. There was one that I used last year. Maybe it's in the online lesson. If I was smart enough and stuck it in there. Okay, you guys got I think you have a setting on the calculator that's just misbehaving at this time. I'll have to do some research and see how we can get around that on your calculators. In the meantime, give me one moment. Let me see if I can find the parametric calculator. I was smart enough and put it into the online lesson. Woohoo! There we go. So in the meantime, here's a different graphing calculator that we can work with in parametric mode. It allows us to enter 3 different parametric equations at the same time. So the first one will be blue, red, and then green. We're going to start with the blue because obviously that's just the first 2 boxes we see. So let's type in 2 cosine of t for x equals, and then try 2 sine of t. We'll just do -10 to +10 for the x range and the y range. And then your t range is going to be 0 to 2 pi. So that one works when we do it. You have to hit plot, I believe, before you can get it to graph. And make sure you're putting parentheses around the t's. So when I first did it, I accidentally did not put parentheses around the t, and it gave me an error. But once I put the parentheses around the t, it worked better. And maybe that was when you go back to your graphing calculator, were you guys well, you said you were copying it identical. You put parentheses around the t in the graphing calculator version, right? Like you put the end parentheses? Okay. All right, that's what I thought because you said you were copying it exactly. I'll have to take a look and see if we can figure out what those dimensions are off by. There's got to be something that's not lining up correctly there. But in the meantime, use this one, this online one, if you need to verify a graph for some reason. This one seems to be working okay. This is also in the online lesson in the resource area. So if you didn't save it or favorite it or bookmark it, whatever you do, you can grab it from the online lesson. So in the meantime, till we figure out your calculator issues, revert back to this online graphing version if you need to graph. Ooh, okay, we got one figured out. But Isaiah said he was in radian mode, so I have to do a little bit more digging with the dimension thing. Okay, again, remember, if we don't get through everything today, that's all right. We'll just pick up wherever we left off in Thursday's class. So let's see if we can sneak in one more topic for today. It says finding parametric equations for a line. This one's actually not that bad. If we're given 2 points A and B, we're just going to start with the first point and turn it into a vector based off of the origin. So really the only thing you need to do is put the little vector arrows around the first point, because if you're taking it from the origin and you're doing the head minus tail rule, you're just subtracting 0 from each of these numbers anyway, and it's not really changing that first vector. So the first thing you got to do is just put the first point into that vector form. So changing parentheses to the little arrows there. The second one, we're going to go ahead and add together two vectors, but we're going to multiply the second vector by a t. So the second vector, we do need to do the head minus tails with the 2 points. So point B is going to be that terminal point, and point A is going to be the initial point. So when we subtract here, we always do B minus A. So 3 minus negative 2, 3 minus negative 2, that turns into a plus sign for a 5. And 6 minus 3 is just a 3. Okay. Any questions up to this point, essentially, on what we did algebraically to get those two vector components? I'll go ahead and distribute that t through the second vector. So doing that, essentially you're just putting a t behind the 5 and the 3. Nothing spectacular there. And then you can add them together. So when I add that together, I get negative 2 plus 5t, and I get 3 plus 3t for the y component. So the first one is the x and the second one is your y. And now you just created your parametric equations for the line there. Okay. Kind of crazy to think about, and this is the parametric, or here's that line, the dashed line, that we essentially created parametric equations for. Okay, not too bad of a concept there. Any questions with that process at all? Woohoo! Okay, I think this is going to be a good time to stop because I'll know exactly where to kind of pick up for Thursday's class. So we only really have one lesson to get through this week, so you guys are still working on 6.02. Hopefully you can get that wrapped up today now that we got that parallel vector thing straightened out. And then we're working through our 6.03 still. So we got the majority of it done. We just need to practice it some more. So in Thursday's class, we'll start off with the practice version of what we didn't get to today. And then I actually was just going to review what we've done so far anyway. So I'll have some review questions for us to look back at lesson 1 and lesson 2 a little bit more as well. Oh, very interesting. Good to know, Isaias. All right. Any other questions for me today before I let you guys go? Okay. If not, take a look at that 6.03 homework assignment before Thursday. Give it a go if you feel comfortable with it. But like I said, we'll practice more with it where we left off at the start of class on Thursday. All right, have a great rest of your day, you guys, and I'll see you Thursday morning again. Bye, everyone.